the time constant tau for an RC circuit. Earlier, we drew graphs for how the charge, current, and voltage across a capacitor varied with time during both charging and discharging. Here, we will make ourselves more aware of the effect of a resistor in the circuit. Sample charging and discharging circuit diagrams are shown at right. When we close this switch, that is going to cause a current that flows in this direction, and we're going to begin charging that capacitor. Once the capacitor is charged, we take the battery out, we close the circuit, and then we're going to have a current that flows in the opposite direction. So the amount of charge will decrease on the plates, the voltage across the plates will decrease, and so on. Here, we will first distinguish between the voltage across the capacitor compared to the voltage across the resistor. When we're charging, the voltage across the capacitor initially is 0, which means all of the voltage is across the resistor. And when this circuit is done charging, the capacitor will have a voltage equal to the voltage of the battery, and the resistor will have no voltage across it because there will be no current, so there can't be any voltage across the resistor if there's no current through the resistor. Now, when we're discharging the voltage across the capacitor, it was a large value, namely the value of the battery, E, so that's where E is right there. And the voltage across the resistor will also change in that fashion because there's no battery in the circuit when we're discharging the capacitor. We remember that whenever we have a graph that looks like this is called a climbing graph, and this is called a decaying graph. I'll just draw arrows like that, and those are decaying graphs. And whenever we have a climbing graph, there should be in the equation for that quantity a term that looks something like this, 1 minus e to the minus something. And our e to the minus something, that's what you've got in any decaying graph. That one right there, and that one right there, and that one right there. A decaying graph has the form e to the minus something. A climbing graph has the form 1 minus e to the minus something. That was a little bit of review. For circuits that have both a resistor and a capacitor, the exponent given above, namely the minus something, is this right here, minus T over RC. And the quantity RC is called the time constant, symbolized by tau. That is, for an RC circuit, tau is equal to R times C. The exponential parts of the time-dependent behavior equations for capacitors are often written like this. This is the climbing pattern graph, and this is the decaying, where in the denominator here we write tau. We could write RC in the denominator of that fraction. From that equation, we see that if we know R and C, then tau is easy to calculate. You just multiply it. Furthermore, it's important to know the value of tau, how many seconds tau is, because it is analogous to another time constant, the one you learned about in chemistry, the one for radioactivity, namely half-life. With a radioactive substance, that is half-life, by what decimal or what fraction does a radioactive substance change during one of the part C answers? Changes by 0.5 or 1/2. If you want to write it as a fraction, who cares? What about during two of these? Well, during two of these half-lives, how much of the radioactive substance still remains in that form after two half-lives? It's only 1/4. This same idea holds for the time constant for RC circuits, except the decimal is different from our part D answer. It's not 0.5. When the time is equal to one time constant, the two decimal places, what do these simplify to? When the time is equal to tau, this is e to the minus 1. And if you type that into your calculator to two decimal places, that fraction comes out to be 0.63. and that fraction comes out to be 0.37. Again, two decimal places. Which one of these is decaying and which one of these is climbing? Well, we know that this is the decaying one, and whenever it has the pattern 1 minus e to the minus something, that is a climbing graph. What about during two of these? Well, if your graph is climbing, it's going to climb up 63% of the way in the first time constant, and in the next time constant, it's going to climb up an additional 63% of whatever's left. Similarly, in one time constant for a decaying graph, it's going to fall to 37% of its initial value, and in the second time constant, it's going to fall 37% of that. To summarize this, in the number of seconds of one time constant, whether climbing or decaying, a quantity will go 63% of the way to wherever it is going to ultimately end up. In other words, it will get 63% of the way there. Whether it's climbing or whether it's falling, in one time constant, it's going to move 63% of the way to its final destination. It'll either rise to 63% of its value if its value is climbing, or it's going to fall 63%. That is, it's going to fall to 37% of its initial value if it's a decaying graph. And in the second time constant, it's going to go another 63% of what's left, and so on and so on.